All right, so let's talk about the official stuff. This is COMSC 142, and today we're going to talk about ARM assembly. But first, a note about grading. I had a student come to one of my office hours last night and say, I've got enough points to get an A. Does that mean I don't need to do anything more? And yes, that's what it means. And I said, well, let me see how many other people are in that position. So I went down here to look at the scoreboard here, and a lot of people have done very well, like they're over 400. And so I went and added all the scores into Canvas. So it's all in one place and you can see how you're doing. And here's the scoreboard. I moved it to the side so you can't see the names of the students, but I filled in this CTF column with the current scoreboard. And as you can see, there are like about 6 students that are over 600. And that's enough. If you go here, here's the grading. 594 or more, you get an A. So those people have done a lot of extra credit projects, and therefore they don't really need to do any more projects or take the final. You're welcome to. I encourage you to if you find it interesting, but you will get an A no matter what you do. Unless you somehow find a way to lose points. I once had someone do this. They actually had an A just barely, and then they took the final and they cheated on the final and got busted. Although now that the final is remote and in Canvas, I'm not sure how that could happen. But you don't need to do anything further to get an A. It just goes by the total number of points. So that's very good, and that was intentional. This means you did a bunch of extra coding, and that's the point of the course. You did some coding. I'm happy. All right, so that's what I wanted to show you about the grading. And there were 2 students who do not have Canvas accounts at all, but are in the automated scoreboard. Anil Kishore and Boofing are 2 names. So if either of those students is in the course, please contact me. You need to make a Canvas account and take quizzes. You need to do a whole lot more than what you're doing to pass. So if those are serious students that want to pass the course, please let me know what's going on with them. Anyway, but they may be people that just have dropped out. I'm not sure. Anyway, let me get to the official stuff, which is here, ARM assembly for today. So all 3 types of assembly follow the same pattern. Oh, let me get my ARM machine going. I'm using my ARM-based MacBook, and I think I'm using this one primarily in this course. I don't know. I have a new one just for Kubernetes, but I think I didn't put much of this course in it. Let's try IPA. The IP address is 0246. Okay, let me get a terminal. Okay, SSH Debian at 246, was that it? Yeah, that was it. And all right, let's see if I have I do, okay, good. All right, and so here I've got some code. All right, this is good. So I can do demonstrations there, and that's a good place for that window that's not going to overlap with my face, which is something to be avoided. Okay, so here we are. All right, so we're going to go through the usual stuff, assembly basics, and then some demonstrations of recursion and buffer overflows and such. So they have the same C source code we've used before. So we have a main routine that calls something called adder2, and adder2 has no local variables at all, so the stack can have size 0, the stack frame. It has a single parameter called a, and it just returns a plus 2. So this sets x equal to 40, calls adder2 of x, and then prints it. So it's very simple. All right. And so if you compile it and then dump it with objdump, you'll see the code. And let me see if I can do that. Objdump minus d. Let's see what I've got here. I've got adder2. And so if I do objdump, let's check to see if my demonstration is set to go here. Adder2, 2.c. Okay, that's the code I just described. It's there. So I've compiled it. So if I do objdump minus d of adder2, which is the runtime version, then I get the code. And here's main, and here's adder2. And so notice what adder2 does. It does a subtraction of the stack pointer to make a stack frame. Then it does a store. We're going to talk about this more in a minute. But store W0 is how parameters come in. Remember, in 32-bit Intel code, parameters go on the stack. But in 64-bit Intel code, they get in various registers. In ARM, they also go in registers, but it's much simpler and easier to understand. It just goes in registers W0 through W7. The first 8 registers are used for the first 8 parameters. So the first parameter is W0, and this function only has one parameter. So I bring in W0. This is the prologue that creates a stack frame. This copies the parameter onto the stack. This then loads the number off the stack back into W0. This then adds 2 to W0, and this then restores the stack frame back to what it was and then returns. So notice that this follows the standard layout of a subroutine, but it's extremely inefficient. You didn't really need to make a stack frame at all. There are no local variables. Here you store the parameter on the stack frame and then just load it back from the stack frame, which is again totally unnecessary. This is interesting. The default compiling just follows conventions and does a bunch of unnecessary extra steps. It'll work, but it's wasteful. That's a thing to notice, but you can see how it works. And down here, you notice BL is the call command, branch something or other, what it stands for. This is what branches to adder to. That's what does a call that goes down here, creates a stack frame, does the calculation, and it returns the value in W0. So W0 is used for the first parameter, and it's also used for the return value, as in 64-bit, it's RAX used for both of those things. So that's, like I say, a lot like the other assembly code we've looked at. One thing to notice, if you look at the actual assembly code here, the actual bytes, you notice in Intel, the instructions have very different lengths. Like a NOP is 1 byte, 90, and a break is 1 byte, CC, and some instructions are 5 bytes long. In ARM, it's always it's always 4 bytes long, every command, always the same. And there is a special ARM thumb mode where it's 2 bytes long, but 4 bytes long is the normal ARM command, which is an interesting, strange thing to do. Okay, so store stores registers into memory, and loads memory into register. And that is one thing that took me a while to get used to with ARM. In Intel, an AT&T syntax for Intel-based processors, it always has the source and the destination in the same order. It's source destination or source destination, but it's not true of ARM. Store will take this register and put it into memory. Load will take that memory and put it in the register. At first, I found that very confusing. So the destination is on the right for a store and on the left for a load, which is kind of annoying, but you get used to it. Notice that you have to have a register here, and this is a general thing about ARM. ARM usually forces you to use registers for everything. If you want to do something to some numbers, you have to first load them into registers, calculate on the registers, and then write the registers out. So it takes more commands. This is typical of a reduced instruction set system. Instead of having a lot of redundant instructions where add assembly, add memory to register, add register to immediate, add memory to immediate, it just only has the simplest one. Just do things on registers, and therefore it'll take more of these small commands to get the job done. See, does the small byte size make it more efficient to use than Intel machines? I don't know if the small byte size is what makes it more efficient to use, but the reduced instruction set definitely makes it more efficient, and ARM processors get a lot more done with a lot less power and a lot less heat generated. And therefore, that's why I say I'm moving to ARM laptops, Apple's moving to ARM laptops, Windows is, and pretty soon everyone's probably going to move to ARM servers. They are more efficient in terms of power and in speed. So this is an argument that's been going on for many decades in computing. There's two philosophies: complex instruction sets where you have thousands of instructions, every possible combination, that's Intel. And ARM is reduced instruction set where you get down to just the minimum necessary instructions and optimize them so they run fast. And then it will take more of those instructions to do the job, but the individual instructions are more efficient. And at the moment, that seems to be winning. I think there's no reason why one of them would have to win. And Intel was the standard for a long time, but Intel as a company has made terrible mistakes in the last few years. So they actually had to throw out their CEO. The last 2 generations of processors had serious defects. They're spinning around the drain. They're in bad financial shape. Although AMD is still doing fine with Intel-compatible processors. But anyway, the whole world seems to be moving away from Intel towards ARM. Although right now, servers are still pretty much running Intel. So right now we need to know them both. But the current industry trend is Intel appears to be on the way out and ARM coming in. And by the way, ARM is proprietary. It's owned by a British company, and you have to pay them licensing to use it. So the open source version is RISC-V, which you'll see in the projects, which is very, very much like ARM. Seems almost identical, but it's open source. It's not licensed, so anybody can use it. And it's becoming the standard in China, mostly due to our hostility with China. We've been blocking China from getting high tech. And so China is not willing to be dependent on the UK since they're part of our bloc being hostile to China. So they're pushing RISC-V real hard in China. So probably there will be good Chinese laptops and everything running RISC-V available pretty soon, and it'll be an option. Right now, you can't buy very good RISC-V hardware yet. It exists, and we do some emulators in some of the projects where you can see how it works, but you can't buy much. You can't buy a practical laptop running RISC-V in America anyway. I think maybe not even in China, but it's coming. Anyway, so you got your registers. It has 31 registers for general purpose, which is really a lot. X0 through X30. There's a few that are special purpose. The program counter is the instruction pointer, tells it which instruction to execute next. SP is the stack pointer. LR is the link register, which is the return address from a function. And ZR is a zero register. It always contains zero. Sort of interesting idea. All right, and so here's the manual. It's actually far more complicated. There's a link here to give you more details. For stack pointer registers, exception link registers, saved program status registers, and so on. There are a lot more details. And of course, there are more details in Intel too. There were a bunch of registers we didn't talk about much, like 128-bit floating point registers and stuff. There are some extra registers. We've only covered the ones you'd normally use here, the main ones. And then there's advanced register notation. ARM, 64-bit ARM, called ARM v8, is an extension of 32-bit ARM v7. Same thing's true of Intel, of course. And so it does support using 32-bit registers if you want to. So you have X0 for the entire register, but there's W0 for the lower 32 bits of the register, if you want to do that. And so most instructions this way: opcode, destination, first and second operand. So that's add. You add into register W0, W0 plus 2, the immediate number 2. That's what this would look like. That's often the way you do it. All right, so you have constant values, have a pound, like pound 02, 0x2, this X means hexadecimal. Registers are written like W0 or a thing like SP to a stack pointer. Memory locations have a square bracket, so this means take SP, add 12, and then you go to that memory address. That's a pointer dereference. So you got X0 as a register, and here we have some example values. X0 contains the value 804. Bracket X0 means go to memory, so that's going to go to that location 804 and find this value CA. You got pound 0x804, that's an immediate value, so that literally means the hexadecimal value 804. You got bracket X0 pound 8, and that means add 8 to X0 and go to that memory location. So X0 is 804, so that's going to be add 8 to it, so it's going to be 80C. That's going to give me 12, okay? And that 12 is hexadecimal, so it's really 16 plus 2 instead of 10 plus 2. Bracket X0, X1, that's going to add X0 and X1, so that's going to be 804 plus C, so that's going to be 810. That'll give me 1E, all right? And X0, X3, and SXTW, this is sign extend memory. So I don't know if I quite understand this one. X0 plus sign extend W3. I'm not quite sure about that one. It may come up in the lecture. I might have to look in the book to learn what that is. That one, I don't remember what it is. Here's scaled memory. This is one we had in Intel 64. So you're going to take left shift by 2 parameters. So you're going to take this number times 4. So you add X0 and you add X2 left shifted twice. So this is going to be X2 times 4. So X0 is 804, X2 is 2, so multiply it by 4, you get 8. This is going to get us to 80C, which will be 12. All right, that one I understand. And here we got sign extend scaled memory again, which I forget exactly what that does. I think, again, it's scaled. All right, it looks like left shifted by 1. Anyway, so those are some complicated ways to add things together to refer to memory by jumps. So you can refer to blocks of memory, as we talked about before. In a 32-bit processor, you naturally want to process 4 bytes at a time, so you often want to jump ahead by 4. In a 64-bit processor like this, you probably often want to jump ahead by 8 bytes at a time because you process 64 bits and you want to go to the next 64 bits. So you have these ways to quickly jump by larger increments than 1. Anyway, here we are. Sign extends the 32-bit W3 to 64 bits. Oh, okay, I understand. So that's because it used W3. I see. So here we have a 64-bit register, and we're adding a 32-bit register to it, and that could be hard to understand, so they do sign extend. So if this is a positive value, you'll pad it from the left by zeros, and if it's a negative value, it's stored in 2's complement, and you'll pad it from left by 1's. That was this sign extend mean. Okay, so the signedness of this matters. So you could have a 32-bit increment added to a 64-bit base. Okay, and here you have a 32-bit increment multiplied by some power of 2, and preserving the sign added to a 64-bit base. So that does make sense. Okay. All right. And so that sign extend. So this is going to take x0 and add the 32-bit W3s with sign extension. So in this case, W3 is 4. So I'm going to do sign extension. It'll just stay equal to 4. So it'd be x0 plus 4, which is going to be 804, 808, which will be FD. Okay. This one is going to do left chip left, pound 2, so it's going to multiply x2 by 4. So x2 is 2, multiply by 4, you get 8. Add that to x0, you'll get 80c, which is 12, okay? Here, of x0, you're going to add a 32-bit value W3, sign extended, and doubled, shifted to left by 1. So that's going to, W3 is 4, so you're going to double it to 8, preserve the sign so it stays positive 8. It's going to be x0 plus 8. That'll be 80c, 12 again. All right, that does make sense. Okay. All right, so data cannot be read or written to memory directly. Instead, you have to first put it in registers, process it in registers, and then write it to memory. You can't just add 4 to a value in memory. That's the penalty of a reduced instruction set. You have to move everything into registers, calculate it there, and then move everything out. So something that might take 1 instruction in Intel might take 3 instructions in ARM. The destination component must always be a register. All right. I could argue about this. The first component is a register, but if you're doing a store, that's actually going to memory. So I'd argue what part they call destination. But anyway, when they defined their terms here, they called this instruction structure, they called this the destination. But then the store command actually writes to memory over here. So I think calling that a destination is kind of a screwy thing for a store command. Like I said, that one command is a little screwy. Anyway, store writes from a register into memory, however you want to say it. Therefore, it writes from the thing they're calling the destination, which is nomenclature I don't like, but that's what they've got. Anyway, so here's common instruction. This loads from memory into a register. This stores from a register into memory. This moves source into destination. This takes O1 an O2, which could be almost anything, and puts the result in D. This subtracts O1 minus O2 and puts that in D, the usual stuff. So this is store into W0, the memory you find by going to stack pointer plus 12. And this loads W0 into the stack, into that memory location on the stack. And this adds 2 to W0 and stores the result in W0. All right, so we just did this. If you just compile this code without optimization, you get this assembly code that does a lot of unnecessary operations. It creates a stack frame, copies the parameter into the stack frame, then pulls it back from the stack, adds 2 to it, and then clears the stack frame and returns. So it does a whole lot of unnecessary steps, but it obeys the standard convention of setting up a stack frame and removing the stack frame. If you just turn on optimization, minus O1, and compile it again, then you get much better code. Here it's just the parameter came in a register, so it's just going to add 2 to it and return. doesn't need to move it to another register or create a stack frame or anything. The smarter optimizing compiler notices that a whole bunch of those operations are not necessary, and you can make a much more efficient code. We'll talk a lot more about this optimization as we go ahead. And there's also these things with P at the end. These will do a pair of operations. So this will take destination 1, destination 2 at x0. So like I say, this will load the value at x0 into D1 and then the value x08 into the next one. So it loads a pair of things all at once, which is pretty nice. So you basically get a 128-bit instruction on a 64-bit processor. And here you get x0 plus 10 and a bang. x0 is x0 10, then sets D1 equal x0 and D2 equal x0 plus 8. Okay, so this actually is a pretty interesting combination instruction. It adds 10 to x0, changing it. I think that's what the exclamation point means. And then it loads x0 and x0 plus 8 into the registers. This will load destination 1 is x0, destination 2 is x0 of 8, then increment x0 by 10. So these two, this adds 10 before you use it, this adds 10 after you use it, and this is the kind of instruction that is pretty surprising to me, sort of combining two instructions into one. Kind of thing I would generally avoid doing just to make my code more readable, but it's an option. And this does the opposite, storing two parameters into this location. So the first one goes in x0, the next one goes in x0 plus 8, and so on. You got these other ones, the same logic as before. All right, and so if you're on ARM hardware, you can get adder2. Here's adder2 with the same code. All right, so if I, let me see why I don't forget what I'm trying to demonstrate this. Okay, we've already done this, the function prolog and so on. Okay, we've seen how the function prolog works. I don't think anything else here is that important. Here's the stack, but it's not that exciting. We can see the stack frame being created is all. This does a subtraction of the stack pointer by 10. So if you then look at stack pointer minus 30, you see some stack areas here. And you're just going to put a W0, which is 40 on there. So you should see, here I'm at the start of the code. So you won't see anything on the stack yet. But after I do this store operation, the value will appear on the stack. And there it is. The 28 will appear on the stack. So I don't think it's necessary to do this live. It's very much like what we've seen before. All right. So then there's arithmetic instructions. Add, subtract, negate, add with carry, subtract with carry, and negate with carry, which is a little strange. I'm not quite sure why you'd have a carry when negating something, but apparently you can. All right. And then you can have, of course, multiply and division. You have unsigned and signed. And then you have composite multiplications, that is addition and multiplication all in one command. So this is kind of surprising to me that they still call this a reduced instruction set computer when it has these, to me, unnecessarily complicated instructions, but that's how it works. And I imagine it's designed to just get the maximum good out of the hardware die. Then you have bit shifts like we talked about before. You have logical or arithmetic, shift left and shift right, and those will multiply and divide by powers of 2, and either preserving the sign or not preserving the sign. And you also have rotate, which rotates the bits around, which is not as simple as multiplying or dividing by 2. And you have bitwise operations, of course, and, or, exclusive or, and this I think is just not. And then a couple of goofy ones down here, I don't remember exactly what they are. This exclusive or and not, or and not, and this one is O1 and not. I don't know why they call it BIC. It's and not. Anyway, so this is some kind of not MVN, which is kind of a strange approximation. Anyway, the main one normally uses and or and exclusive or. These exotic ones are ones I wouldn't use willingly, but a compiler might use them. All right, let's try a Kahoot. 9A. That's to the left, so hopefully the number will be there. Number is visible. Good. All right. Well, you may have only 3 competitors. That appears to be the case. We shall charge ahead. Oh, there we are. That makes a little bit more of a contest out of it. If there's more than 3, I'll wait another line or 2 of the song. I think they're measures. Anyway, all right. All right, so which instruction stores data from register into memory? This one. This one goes from register into another register. The brackets are what takes you from this register into memory pointed to by the value of x1. And the loads do the opposite. They load from memory into a register. So it's this one. All right. All right, how long are ARM v8 instructions? They are always 32 bits, which is a little strange. You would think if they're going to have a 64-bit address or something, they'd have to be longer, but somehow they always fit it in 32 bits. So that's one of the screwy things about ARM code. Apparently, that makes it more efficient. All right, and what does ZR contain? Ah, I remember. I remember, but I don't really know why this is a good thing to have. But again, I suppose it makes it more efficient. It's a 0 register that always contains 0. I don't know what you'd need that for, but the end result is ARM is very efficient, so I imagine it serves some internal purpose. All right. Good. All right. So then we'll talk about conditional control and loops. So you have a compare and test commands, both of which compare them in various ways. This does subtraction. This does an AND operation. They're ways to compare things and see if they're equal. These do not modify anything. They don't save the result anywhere. They just change the flags. So I generally use compare. I'm used to that. I compare them, and then I can branch whether it was greater than, less than, or 0. Then you need a branch instruction. B is an unconditional branch. B, this branch goes to an address. This is how you enter a subroutine, a function. You change the program counter to point to that address. Here you do, if R is equal to 0, then go there. It's a conditional branch. And here's another conditional branch and another conditional branch. So that's another way to do things. We had a conditional move in Intel 64, and there's conditional branches here. So this would combine sort of an if and a branch in the same one assembly language instruction, which sounds pretty handy. And then you got suffixes. So sign comparance is equal, not equal, minus, plus, greater than or equal to, and so on, the usual sort of thing. Same stuff you'd see in 64-bit Intel with slightly different words used for it. So here's if statements in assembly. So here I have a function with two parameters, x and y. If x is greater than y, then it sets this to the smallest, otherwise it sets it to x. So here's the code. So here I am creating a stack frame with this prologue. Now I'm putting the two parameters which come in as W0 and W1, storing them on the stack, and then loading them back from the stack. So you can already tell this stuff was probably created by non-optimized compiling. It's done some unnecessary motions here. Then it's going to do a comparison, which is going to be W1 minus W0. And if its branch is less equal, it will jump down to here, less than or equal. Otherwise, it'll go here. And so now it will load W0 from this stack location and write it here. So stack plus 28 is apparently going to be the result. And then it's going to have an unconditional branch to jump down to 24, where it's going to load it from that location 28 and return it. So you can see already that this is like the unoptimized one. It did a whole lot of unnecessary things here. You know, it could have ignored the stack entirely and just used W1 and W0, just compared them, and then returned the one that was smaller. You know, I think it would take about 3 commands to do this efficiently. Do a comparison. If W0 is smaller, just return right away, because W0 is the return value. Otherwise, store W0 to W1 and return. So I think you could do this with 3 commands in an optimized compiler, but this obeys all the conventions of creating a stack frame, storing everything locally, processing locally, you know. All right. So it'll get the job done, but it's far from efficient. And here's the annotation, which I think we've already been through. That one's pretty easy to just read, which is the point of this class. Hopefully you're getting ready to read your assembly code. So here we do the comparison. That's the important thing. And here we could do a conditional select. Is another way to do it. So this would do a conditional select. If x less than or equal to y, W0 equals else W1 equals y. So that's right. This one command will sort of do the whole thing, which is pretty nice. Although I don't quite understand why it's mixed with this one. So this must be, it looks like another way to do it with a conditional select. This is probably with some optimization turned on. All right, and then we can have loops. So here's one loop where you have while I is less than or equal to n, add the total, add I, and then return. Here you do a for loop. For I equals 1, I less than n, total I equals 1. Therefore, I will increment because of a for statement, and the total will increment down here. They're both going to do the same thing in assembly code. They look different in C, but they're going to compile to the same assembly code. So here we are, make a stack frame, store the parameter on the stack, store WZR. This is the 0 register. Oh, that's interesting. So store a 64-bit 0 there. So you can initialize something. Okay. And it occurs to me that this might be answering something I brought up before. If you have 64-bit registers and yet the instructions are only 32 bits long, I don't see how you could possibly have an immediate 64-bit value. So that might be why you want to have a 0 register. That's a 64-bit value, easily reachable. Anyway, so here's going to set W0 to equal to 1. This is also going to store that 1 somewhere on the stack. Then it's going to jump to plus 52 way down here. And that's going to have a branch less than or equal that comes back up to 24. So this is the loop. So W1 is total, and off you go. You see the usual stuff. This increments the total, stores the result in total, and it's very much like the assembly we've seen before. That's going to be the loop. All right. And then you got functions in assembly. We talked about them. BL is what goes to a function. And this sets x30 to PC plus 4. There's another fun fact. Since all the instructions are 4 bytes long, the PC plus 4 is the next instruction in line. So this is the return pointer, which they stuck in x30, which is a register, and then set PC equal to address. And here's BLR. This will do the same thing and then set PC equal R, so it'll jump to the register instead of immediate address. 2 different ways to do it. And here's return value, of course, very much like it has been in Intel. The first 8 parameters are in the first 8 registers, which is very handy, easy to remember. cleaner than the Intel system where they were in a strange pattern of alphabetical registers. If you need more than 7 parameters, then it loads onto the call stack. So here we got adder. Here's the function we've seen before where we have a main function, and it's going to call assign and then adder. And assign is going to decline a local variable and return it. And adder is going to use a local variable without initializing it, so it will find the leftover value of this one on the stack. We've done this one before, and again, I think it's not really worth doing live. Here's your code. Here's ready to prepare a stack frame, and here's the area of the stack which nothing on it yet. And then if you go forward a few commands, it's created the stack frame and it stored this 28 locally, because that's the assign function. So it puts it on the stack and returns it. And then when you go to the adder function, here it is loading something from the stack frame without having put anything on the stack frame. So it assumes that the parameter was pushed on the stack, or it assumed it was already there, forgot to initialize, and it finds the value that was left over there by the previous function. So the same logic applies. You end up adding a remnant value using remnant data in memory. All right. So, and then of course there's recursion, the same as we saw it before. You can make a summer function. It's going to add up numbers by calling summer, calculating summer of n in terms of summer of n minus 1. So when you calculate it with, say, value of 4, it's going to end up with multiple stack frames from the same code. As you call the same function again and again, calling itself, it'll lay a pile of stack frames, evaluate them, and then pop back from all these stack frames, just like we saw before. Works the same as Intel code. All right. And arrays, you'd have like an integer array or an integer pointer array, or in general type, any kind of variable type array in C. So here, if we have examples, x1 contains the address of array, x2 contains I, and x0 contains x. So here you set x equal to the pointer to the array. That's move x1 to x0. x1 is the pointer to the array. This put x. Then here's x is array 0. That's the same thing. But why is this x and this is w, which is only 32 bits? Because it's int instead of int star, and I guess int is only 32 bits. Okay, so, oh, that's right. X is the first element of the array, not a pointer. Okay, so this will find the first element and load it in a 32-bit integer, because I guess it's int. Okay, then here's the x array 1. That's going to be x1, and x2 contains I, and that's going to be counting by 2 left shifts, moving up by 4 bytes at a time because the integer is 4 bytes wide. Okay, so this I will be the base value plus 4 times the index. Okay, and here you have a pointer to array 3, so you have to take the start of the array and add 12, and then add x0. And notice it is a pound without the 0x, so this is the decimal value 12, not the hex value 1, 2, which would be 18. And here you have array plus 3, which is going to be the same, because remember C knows that when you add to the pointer of an array, it counts by the size of the array elements, not just by bytes. And here you have a pointer to the 5th element of the array, so that's going to be 20 bytes from the start. So that's, I think, same thing we've seen for other assembly languages, quite similar. So this is an array with 10 integer elements. Each one of them is 4 bytes long, so this is going to take 40 bytes to store all that. And you can have matrices. We're skipping them, 2-dimensional matrices in assembly. I have no reason to get into that madness. For that, I would use a higher level language, I would think. Although, of course, you can do it in assembler. You can, in principle, do anything in assembler, but, you know, for complicated stuff, it makes more sense to use a higher level language like Python or C. And structures, of course. Since you have arrays, you can have other structures just like before, like this one we had before, 64-character name, then a couple of integers, then a floating point variable, and it will just lay them out in memory just like it did in previous assembly languages, and you can then refer to it here in structure. And so as far as assembly goes, it's just the same. You just refer to them all by offsets. So here it is, x29 appears to be the register where you put in the stack pointer, so that's where it's going to start. And then you just refer everything to that and move forward by different offsets as you store these various parameters in there. So, that's all these store operations do, is write to the correct memory location. All right. And there's data alignment again, as we said. So if you have a 63-character string followed by integers, you still have the padding. It still wants to put 4-byte integers on a 4-byte boundary. That's the same in ARM assembly as it was in Intel. All right. And then you got buffer overflows. This is probably worth doing live. So let me see if I've got this secret ARM64. I think I do have it. Let me see where I am. All right. Clear and ls. I do have secret arm64.tar.gz1, so I unzipped it, and it's in this directory. Okay. All right. And so now I've got a secret to run. All right. So I run the secret in here. It asks me for a number. When I give it 1, it tells me I'm wrong. And of course, I want to try to exploit some kind of buffer overflow. So what if I give it A? Doesn't complain. What if I give it A? Okay, that doesn't give me an overflow. Let's run it again and put in a longer one. So HIJKL. Now I get an error. So this seems to be enough to overrun it. All right, I'm going to put that on my clipboard. Let's go back to my notes. Okay, looks like before I thought an I would be enough. So let me just see if I can do that. I just needed a little more than this one. Okay, so let's run that and just put in the I's. And put that in my clipboard. Okay, that's enough to have a bus error, which I hope is something like an overflow, something like, a segmentation fault. Perhaps that's exploitable. So we have partial source code. And you see here I have a buffer of 12 characters, and I enter the number, which is read in as a string. So I'm putting in more than 12. As you can see, a lot more than 12, and then it crashes. All right, so I did all that. All right, and now if I run it in the debugger and put in the I's and the J's, then we'll see that it ends up in the instruction pointer. So GDB minus Q secret. Oops, got to spell it better. Secret. Okay. Now run, put in this stuff and also the JJJJ, okay, and it crashes. And see, here's the instruction pointer, which is 4949 4A 4A. So this is 41, 2, 3, 4, 5, 6, 7, 8, 9A. So these are the I's, and the first 3 J's are what ended up in there. So this ends up in the instruction pointer, and I should be able to see that if I do info registers. Here's all my registers, and one of these is going to be the instruction pointer. Here's the program counter, and as you can see, there it is. It's 49 4 times and 4A 3 times. So the I's and 3 of the J's ended up in the program counter, so I should be able to control the box and take it over. And that's the goal. So we'll disassemble endgame to find the address we want. So it's disassemble endgame. All right, so there's the address I want. And now I just could be able to create code that will do that. So let me go back out of the debugger and turn off the address space layout randomization. I'm going to copy that long command that I can't remember. I have to do sudo su minus to move up to root and stay there. Give it my password, which I got to spell better. Now I can execute that command to turn it off and come back to here. And all right, that should have gotten rid of address space layout randomization. And now I should have a secret exploit. Let's take a look at that. I do have it, so cat secret exploit. All right, and so all I did was relating this. I know the next bytes are going to go in there, so here's the data I put in there, and that's going to be that address that I saw up here. They're ending in EC08 and a bunch of A's. So it's EC08 and a bunch of A's. I feed in that stuff. And so that should do it. So if I run that exploit into the code, I should be able to run secret and take the data from running that thing, which is secret exploits. Just copy it from here, there. This should do it. That should run it and feed it into the program. And looks like I forgot to make it executable. Let's do chmod plus x secret exploits. Okay, now this one should work. And ambiguous redirector, it looks like a prefix didn't like it very much. I could probably do it this way. I could run Python 3 before that. Yep. All right, anyway, let me see my notes and find out how I did it. Okay, I put it in an exploit file. That's probably the way to do it. So I run it. Let's see, Control C. Let's see if I can run secret exploit. And okay, that's the problem. I do Python secret exploit. Okay, Python 3 perhaps. All right, there are different versions of everything. There we go. That prints out the stuff. So I take that and put it in, say, AX. And now I have to do ls minus L. There's a file called EX. And if I examine it with XXD, I can see what it is. It's all this stuff. And then at the end, it has that address, EC08, and a bunch of A's. So now if I run secret, and I take the data from EX, there we go. I win. You win. Okay, so that's what I wanted to show you. All right. So that's a typical buffer overflow showing there. Now exactly why it ended up there is not clear. We didn't see the source code. And one thing about ARM exploits is that the return value is not typically stored on the stack. So what I actually find is to exploit ARM exploits, you have to be in a subroutine, and you have to put in so long of an injection that you actually hit the return pointer from main. So it is a little more complicated and difficult than it is on Intel-based systems to exploit a buffer overflow, but you can sometimes get away with it like we did there. And so here's defenses, address space layout randomization, randomly locates in RAM. We've talked about it before, so you can't find an address to jump to like I just did. That's why I had to turn it off for that demo. Stack canaries, put a value at the end of each of the stack frame so it will notice when it tries to return from a function. If that value has changed, it will stop, saying the stack has been corrupted and I can't trust that return pointer anymore. Which I wonder if this even exists in ARM code or if it would work, because ARM code doesn't store the return pointer on the stack anyway, but maybe it does apply it to the main routine. And then data execution prevention implements the NX bit in the motherboard of the computer, which allows you to mark regions of memory with permissions so you enforce write or execute. Every segment can only have write or execute turned on, not both. So anything that lets you add in data cannot execute, and that'll stop you from injecting code. And there are safer C functions we talked about before. Instead of using getS and scanf and string copy, use versions of them that limit how much data you feed in, so your programmer is hopefully reminded to control how many bytes are read and make sure only enough bytes are read to fit into the memory you reserved. This has been around for decades, and it has been extremely ineffective at stopping these vulnerabilities, which is why, as I mentioned before, a lot of people are just getting fed up with C and C++ and just moving to Rust, which prevents all this in the structure of the language. It doesn't place so much burden on the programmer to try to remember these pitfalls and avoid them. And so here's the safer source code where when you scan it, you scan only 12 characters, so you don't let it be longer than that. Although, I must say, you only reserved 12 characters. You forgot to save one extra for the null pointer, so I think there still might be a certain degree of flaw possible here. But anyway, you certainly can't do the kind of buffer overflow that we just did. So let's take a look at a Kahoot, which is this one here. All right. 2 measures per line. I don't think there is a term for the line, official music term. All right, guess we got 3 competitors. All right, so which instruction will jump, but only if the previous instruction resulted in 0? Branch equals. That branches if you're equal to 0. This is branch less than 0, I think. This is unconditional. And I forget what BLR is. Let me just check my slides. That's interesting. What is a BLR? Wonder if it's in here. I think it would be. I try to always use real things. See if I can find out what a BLR is. Loops. If statements. Okay, here they are. PL, L equal, LS, BLE. I'm not seeing a BLR. I wonder if that's actually a typo or something. I don't know what that would be. LS is okay, and LE and LT and LO. Yeah, I'm just not learning what a BLR is. I'm skeptical. That might be an invalid one. Anyway, all right. All right. All right, which one is a normal function call? It's BL. Wait, it's B. Oh. That's an unconditional branch. Now, wait a minute. The right answer is BL. There we are. I'm just confused by everybody getting it wrong. B is an unconditional branch. That is go to. That is go there and never come back. It doesn't save the return pointer anywhere. BL is the normal function call, and I don't know what the L stands for. I just know from assembly code this is what you use instead of call. BL is what branches and it saves the return pointer. That's probably what the L is, something like a link register or something. That's what it is. This means go there, but save the return pointer in a register and come back on a return. You use this, you're never coming back. That's go to. All right. So, all right, which security measure marks memory regions non-executable? That's data execution prevention. That's the Microsoft term for it. And it's pretty clear from the name. That means regions that are data that you can write to are not executable. That's what it is. Stack canaries mark the end of a stack frame to detect if there's been a buffer overflow. That's quite different. Anyway, all right. So, all right, I got 3 for OB1. I may not know who that is. Helene, I know who that is. Maybe. All right, so I got that stuff recorded. Let me stop the video.